Hey everyone, it's Dr. C. Happy snowy Friday. I guess it's good that we're getting some moisture, so good for the forest. All right, so let's pick up where we left off in class. And we really got into an important type of problem, an important problem-solving technique. I guess we can call it even a concept of some sort. We're going to deal with this concept of an ice table quite a bit over the next month. This chapter, we're looking at gas phase reactions for the most part. The next chapter is going to be acids and bases, where we'll use this setup for weak acids and weak bases. Okay? We're then going to get into the next chapter. We're going to deal with buffers, where equilibrium will come into play for buffers as well. And then we're also going to look at solubility of salts, ionic compounds. Ice tables are going to be involved with that as well. So we're going to look at a lot of different reactions that all involve equilibrium, and we're going to set them up this way. So really try to get a good grasp on this idea of an ice table and how we solve for X and set this up. All right, so let's review where we left off in class on Thursday. And we kind of rushed a little bit at the end of class, but we pretty much got done with this problem. But let's review. We're given an equilibrium constant. We're given a reaction. And then we start, so initially we start with 2 moles of CO2 in a 5-liter vessel. So that's how we came up with this 0.4 molar of CO2 to start. It doesn't say anything about the product, so we assume there are no products present in that reaction vessel. All right. Now here's a key concept. Because we're only starting with reactant, the reaction has to initially proceed to the right. I don't know why my pen's not working very well. So it proceeds to the right. Now we know equilibrium means we have a forward direction and a reverse direction. But if there's no product, there can't be a reverse direction first. We have to go in the forward direction. Once products start building up, then it can start going back in the reverse direction. So initially, it has to go to the right. It has to go to products. So that means the amount of reactant is going to decrease. And that's why there's a negative sign there. All right. The other thing to notice is the coefficient. We're going to see the coefficient there in terms of our variable. All right. We are going to produce product in this case. There was no product at the start. We know we're going to have some product at equilibrium. We have to produce product. Again, the coefficient of 2 comes into play. Coefficient of 1 for O2. Okay, so we just see plus X. All right, and let me get rid of that underneath. That looks like plus or minus X. Let me get rid of that. Okay, well. All right, and then we have initial. We know there's going to be some change. We just add those two together. 0.4 minus 2X. 0 plus 2X is just 2X. 0 plus X is just X. All right? So that's the ice table. Really, really important that you can set that up, because if you don't set it up right, guess what's going to happen? Yeah, you're not going to get the problem right. Because we're going to take those values in terms of X, and we are now going to take those, and we're going to plug those in to our equilibrium constant expression. All right, so make sure you can write the expression. It's just products raised to the power of the coefficients over reactants raised to the power of the coefficients. We multiply things together in the equation, so the two products are multiplied. We then plug in. We plug in our equilibrium constant. We plug in our amount of CO in terms of X. Note that 2 there. So look at that. We see that coefficient of 2 in the exponent, and we also see it in the 2X term. So be careful there. You're going to see it in 2 places. The amount of O2 is just X. The amount of CO2 is 0.4 minus 2X. Again, we see that coefficient again. We then try to solve this equation. In this case, we just went to 2x squared times x is 4x cubed. So that's all we did to simplify to this next step here. Now, this is a cubic equation. And some of you do have calculators that would solve that. But we're going to make a very important assumption quite a bit going forward. All right? If we have a very small k, and by very small, we're typically talking, certainly 10 to the minus fourth or smaller. But if you're in the 10 to the minus fifth, 10 to the minus sixth range, typically that's small enough. Okay? And that magnitude is important because it tells us that at equilibrium, small k, mostly reactant at equilibrium. Mostly reactant. Therefore, this amount, which we show here as 2x, going to product, is going to be really, really small. All right? Yes, some reactant is going to go to product, but not much. And again, this is a key assumption. So little is going to go to product that we assume that 0.4 minus a really small number is going to stay approximately 0.4. It will decrease. It's not going to stay 0.4. But, our hope is that our k is small enough that it'll stay close enough to 0.4 that it won't affect our calculation very much. Again, this is an approximation, but it will greatly simplify our calculation. So instead of 0.4 minus 2x here, we just have 0.4. Still going to be squared, so don't forget that squared term. Now solving this equation becomes much easier. We cross multiply. We get 3.2 times 10 to the negative 7th is 4x cubed. We divide by 4, get 8.10 to the negative 8.8 times 10 to the negative 8th is equal to x cubed. Take the cube root, and we get x is equal to 0.00431 molar. Okay? Okay, very important problem. Really focus on this. Make sure you really understand this. In class on Tuesday, I'll take any questions that you might have on these problems, even this problem. We'll go back to this one and just say, is there anything that's still confusing you? All right. So now for the pre-lecture quiz. This one's already solved, but we haven't finished this problem. Okay. So x in our table, there's x. That happens to be the concentration of O2, equilibrium concentration. Again, E is equilibrium. That is the equilibrium concentration of O2. So we have that. But what about the equilibrium concentration of CO? Oh, that's 2x. So all we have to do is multiply that by 2. And then our equilibrium concentration, I'm sorry, I've got so many different colors and so many things written on here. The equilibrium concentration of CO2 is 0.4 minus 2x. So once you get this 2x value, to get the concentration of CO2, just subtract that 2x value from 0.4, see what you get. So that'll be 2 questions on the pre-lecture quiz. What's the equilibrium concentration of CO? I think you can do that. What's the equilibrium concentration of CO2? Well, you already have your x value, so plug into your table and solve. All right, let's do one more thing here. I think I've gone for about 8 minutes. Let's look at this next problem. And let me put this on a separate page so that I don't have to be fighting between pages here. All right. Sorry, it appears my computer is updating. Probably a Microsoft update right now, so it's running very slowly with this recording software going too. All right, so let's set this one up. Again, it's good to rewrite the reaction. And our ice tables will always have the same form. We'll have an initial. All right, so let's see what we have. The initial pressure of NO in a reaction vessel is 0.8 atmospheres. NO, oh, it's our product. That's okay, because we know we have, although my arrow's not showing here, we have both a forward I'm sorry. I think there's an update going on, and so things are being very finicky with me right now. We know there's both a forward direction and a reverse direction. So in this case, it doesn't say anything about a reactant, so we assume those are 0. So this one, and don't be confused by this, we're going to see this quite often with equilibrium. Since there's both a reverse and a forward direction, if we start with product, it's going to have to go in the reverse direction first. It's going to have to go to the left first. All right? The other thing not to be confused about is the unit of atmospheres. We are given kp, not kc, So we do need to work with pressure as our unit of concentration. All right, well, let's do our change now. Since, I really apologize, this is not working very well at all. Since we have just product to start, no reactant, it has to go to the left. So our amount of product has to decrease. That has to be a negative 2x because we have to produce our reactant. And watch your coefficients. We have a coefficient of 2. So we're going to have to factor that in with that negative 2x term. Therefore, at equilibrium, our concentration of N2 is just x our concentration of O2, x, our concentration of NO, 0.8 minus 2x. There's your ice table. They're all going to be a little bit different depending on coefficients and what your starting amounts are, but the concept of setting that up is really crucial. Now we can write our Kp expression. Kp, the only difference between Kp and Kc is our unit of concentration, pressure of NO squared. We still have to raise to the power of the coefficient over pressure of N2 times pressure of O2. Plug in. 0.05 is equal to 0.8 minus 2x squared over pressure of N2 is x, pressure of O2 is x, so x times x, x squared. All right. Now we look at this equation. This one, if we multiply this all out, FOIL out your numerator there, we're going to end up with a quadratic equation, which we could solve without a graphing calculator to solve it for us. And at some point in this course, probably maybe even on Tuesday, we will solve one where we do fully solve a quadratic equation. But a lot of times we're going to be able to make simplifications. All right. Now this one, we don't have a small k, so we can't do what we did up in the previous problem. And besides, we're not starting with reactant, we're starting with product. So we can't make that same assumption. But this is something else to look for in terms of simplifying calculations. Let me switch pen color here. We have a squared term in the numerator. We also have a squared term in the denominator. Oh, that's kind of nice. Since those are both squared, we can take the square root of that. Now, since we took the square root of that side, we have to take the square root of the other side of the equation as well. But since the numerator is squared, that's just going to reduce to 0.8 minus 2x, okay, because that was squared and we took the square root of it. So in effect, the square root is raising to the 1/2 power. So in effect, we're taking 2 raised to the 1/2 power, which is just going to be 1. So we end up with 0.8 minus 2x, and the square root of x squared is just x. How beautiful is that? All right, square root of 0.05. We still have to do that on the left-hand side. And that is going to be 0.2236. All right, and I'm going to keep, it's actually 0.22361. Let's add another digit just to be safe. All right, cross multiply. Got to do a little algebra here. All right, add 2x to both sides. So then we're going to get 2.22361x is equal to 0.8. Divide by 2.22361. Let me add 2 to that. And I get an x value of 0.35. Well, let's see, how many sig figs do we have? We really only have 2, it looks like. So I'm going to round this to 2 for now. Yeah, so 0.050 and 0.80. So to 2 sig figs. I can get my eraser here. 0.36. And what is my unit here? Remember, we work with Kp, so these equilibrium amounts are going to be in atmospheres. Okay, Kc, molarity, Kp, pressure, atmospheres. All right, are we done? What are we supposed to answer here? What are the partial pressures? Now, don't get confused by partial pressure. Since we have a mixture of gases, we call the pressure of each one of those gases a partial pressure, and those partial pressures of NO, N2, and O2 make up the total pressure of that system. So that's what partial pressure means. So we want the equilibrium pressures of all of these guys. Okay? So, N2 and O2, I think you got them. You might see that on the pre-lecture quiz. What about the pressure of NO at equilibrium? Yeah, 0.8 minus 2x. You have x. We got to take 0.8 minus 2x. Solve for that. All right. One last point for this pre-lecture, because I think I've gone over 15 minutes. Once you get these values, so once you get the pressure of N2, the pressure of O2, the pressure of NO, it's always good practice to take those values that you solve for here and plug them back into your Kp expression up here. So once you have your equilibrium pressure of NO, plug it back in and square it. Plug in your pressure of N2, plug in your pressure of O2, calculate that, get a Kp value, and it should be very close to that 0.05. It might be slightly different because of rounding errors, but you should get that same K value. Always good practice. You can double check yourself on a lot of these calculations. All right, if you watch this pre-lecture video, you should do well on the quiz. It's just going to pertain to these two problems. Can you solve for these equilibrium concentrations? I think that's going to be pretty easy since we've pretty much finished these problems. Again, in class on Tuesday of next week, come to class prepared to ask any questions on these. It's really important that you get a handle on this right now, right at the start of equilibrium, because we're going to be spending a lot of time doing various types of equilibrium problems, acid-base, buffers, solubility, going forward. All right, enough for now. Enjoy the snow. Hopefully it'll warm up again soon, and we'll have an early spring. We can only hope. All right, have a nice weekend. Take care.